Welcome back to your next exciting 3-3 linearity and continuity adventure. Are you ready? I hope you're all sitting down because this is going to get pretty exciting. These are your practice problems, okay? We'll start on page 163. Let me move my little camera down so you can see the page number. We're going to be starting on page 163. Remember, these are either discrete, continuous, or neither. Okay, and it has to be all or nothing or else it's just neither. Okay, so number one, is it discrete, continuous, or neither? It is neither. You're right. It's neither because it has continuous parts, but the whole thing is not continuous. So this is neither. Now number two doesn't have any continuous parts. So number two is considered to be discrete. Very discrete, yes. Number three is also discrete. The points are not connected at all. Number four is continuous because all the points are connected. Number five is continuous because all the points are connected. Number six has some connected parts and some not connected parts, so we have to say neither or neither, however you'd like to say it. That's not continuous or discrete. It's a mishmash. Number seven is discrete because it's just a bunch of dots that are not connected. Number eight is continuous. This is one I alluded to in an earlier video. This is, even though it does have a weird little bend in it, they consider this a curve, and they say that this is continuous because everything's connected. Now, this would not be linear, but we're not worried about that on these problems. These problems, they're just asking you for discrete, continuous, or neither. All right. Kylie records the number of hours she works in her after-school job each week and then graphs the function that models the situation. Use the graph to determine if the function that models this situation is discrete, continuous, or neither. They could have just gave us the graph and said, is this... They have to add in a little word problem. Is this discrete, continuous, or neither? You're right. It's discrete. Oh, we have another little story with a graph. Kalinda keeps track of the number of cups of flour she has after baking batches of cookies and then graphs the function that model. Kalinda needs to get a life. Seriously. Use the graph to determine if the function that models this situation is discrete, continuous, or neither. This is continuous. Yes. Okay. Should I even read this? Seriously. Well, if they would put like names I could print, Nayati? I guess. Nayati records the number of hours of homework he has each day and then graphs the function that models the situation. Use the graph to determine if the function that models this situation is discrete, continuous, or neither. Discrete. This is the hardest lesson we've done all year, right? All right, now we're talking. Now we have some equations that they want to know if they're linear or nonlinear. So this is where it gets fun. I'm excited now. So excited. Okay, first of all, when I told you earlier that all variables had to be to the first power, and I might have even said positive 1 power, this one is not going to be linear, and the reason why is when x is in the denominator, that means you have an x to the negative 1 power. That is not an x to the positive 1 power. This is nonlinear. Now, I could simplify this a little bit. I need to have that x on the other side, so I could add 1 over x to both sides, and then I would have y equals 1 over x plus 11, but it's still nonlinear because that x is still in the denominator. There's no way for me to make that get fixed, okay? So it's nonlinear. This one is a beautiful example of a linear equation. Both, first of all, it's in y equals mx plus b form, and both the x and the y are to the positive 1 power. That's linear. Number 6, I know I'm going out of order, but I'm going to do these ones and then I'm going to slide them over, okay? Do it like that. All right. This one, the x is in the top. Okay, so that makes a difference. Let me erase this stuff right here. Okay, and now go back to pen. Okay, this one makes it, that makes a difference. This is 2y plus x over 3 equals negative 6. First of all, this is x over 3. This can also be written as 1/3 x. So let's say it's 2y plus 1/3 x equals negative 6. This x is to the first power. If it had been in the denominator, it would have been to the negative 1 power. But because it was in the numerator, it's to the positive 1 power. And that's what we want for linear. We want to get y by itself, so I subtract 1/3 x from both sides. That will give me 2y equals negative 1/3 x minus 6. Then I need to divide every term by 2. Okay, divide by 2, divide by 2, divide by 2, and I'll end up with y equals negative 1/6 x minus 3. This is a linear equation, boys and girls. X and y are both to the positive 1 power. This line has a slope of negative 1/6 and a y-intercept of negative 3. That is a line all the way. Line, ear. Okay. I'm having a good time. You know what? I love doing math problems, and today I'm getting paid to do math problems, so it just doesn't get any better than that. If you love doing math problems too, maybe you should become a math teacher and get paid to do math. It's great. Oh, look at number 18. Oh, buddy, it's got some stuff going on, doesn't it? Ooh, let's do this first. When we're working with parentheses, we do what's inside the parentheses first. So we're going to have negative 9x plus, in parentheses, the square root of 4 is 2x, and that's squared, plus y equals negative 4 plus 7x squared. Alrighty? Well, I see how some stuff's going to go down here. All right? Check this out. We distribute this 2 to both of these. This becomes negative 9x plus 4x squared plus y equals negative 4 plus 7x squared. I'm getting the feeling these x squareds are not going away, okay? If we want to get all of our x's on one side, let's go ahead and move these 2 over to this side. So we'll just be left with this nice little y, because we're really getting to the y equals mx plus b format is where we want to be. So I would have to add 9x to both sides, and I would have to subtract 4x squared from both sides. And then I already had minus 4 plus 7x squared on the right. This was already on the right. And I got these 2 terms on the right by adding this one to both sides and subtracting this one from both sides. Now we can do some cleanup. 7x squared and negative 4x squared is going to give us 3x squared. And then there's no one to combine with the 9x, and there's no one to combine with the 4. This is not linear, boys and girls. This 3x squared is not going anywhere. And because that x is raised to a power other than positive 1, this is not linear or nonlinear. I'm just going to write this, and then I'm going to erase it. So I'm kind of wasting my time, but that one's nonlinear. Okay. But it might not be a waste of time, because you know these problems always appear on the practice on McGraw-Hill. They do, almost exactly these problems. Okay, so now we're going to look at these oddballs over here. Times, oh, number 13. That looks like a world of fun. Let's simplify this a little bit. We have x plus, and we're going to distribute this 2. No, let's do this first. Square root of 2. What's the square root of 2? Square root of 2 squared. Those cancel each other out. When you square a square root, those are inverse operations. So this is going to end up just being 2. This x is not under the square root symbol, so we're just going to go, we're going to square this x with that square right there. Sorry, I'm probably not explaining this very well. Plus y minus 2x squared equals 11. Now we can combine like terms, and look what they did here. 2x squared minus 2x squared, those are going to drop out, and we're going to have just x plus y equals 11. To get it into slope-intercept form, we just subtract x from both sides, and we have y equals negative x plus 11, and this is a straight line. X and y are both to the positive 1 power. The second power dropped out. Okay? So that is linear. Number 15. Oh, number 15, there's just no hope for this guy. This 3x squared, this thing is as simple as we can make it, and that 3x squared is not going anywhere, so this is non-linear. This one was linear. Okay. What about this one? Well, they're trying to trick you. This one is nonlinear too. Once you square that x, that's going to be x squared, and there's going to be no getting rid of that one. But I can go ahead and do the problem a little for you so you can get the idea here. 9x minus 9 squared is 81, x squared is x squared, equals 19 minus y. All right. We want to get y on one side by itself. We can add y to both sides. We can add 81x squared to both sides. We can subtract 9x from both sides. And then we still have the plus 19 hanging out over here, chilling like a villain. We're just not getting rid of this x squared. And because we have an x or a y to a power other than positive 1, this is nonlinear. Okay. Same with number 19. There's just not going to be any fixing this x to the third. There's no other x to the third to add to it to make it disappear or anything. So this one is also non-linear. Ooh, buddy. Yep. Okay. Next, we have little tables. Remember, with tables, we're looking for a constant rate of change. A constant rate of change indicates a straight line. Okay. From here to here, this is an increase of 1. 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 These all increased at the same rate. From here to here, this is an increase of 25. Increase of 25. Increase of 25. Increase of 25. This one is linear. The rate of change is constant. That makes a straight line. This one, increase by 1, increase by 1, increase by 1. Phone call. Got to put this on pause real quick. Sorry about that. My patio guy was calling me, and I'm super excited. I have wanted a patio in my backyard for like 20 years, and I'm finally getting one. And he was calling to tell me he's going to put it in next week. So excited. All right, so where was I? I was checking this little table here. This is also an increase of 1. Over here, this increases by 2, and this increases by 6. That's all the further we have to go. In order to be linear, all of them have to be exactly the same. To be nonlinear, just one of them's got to go bad. So this one is nonlinear. Okay, I'm going to have a patio. And then winter will hit, and I won't even be able to use it. Okay, so this one went up by 3. This went up by 2. Oh, they're going to make this difficult for us. This went up by 2, and this went up by 1. So now we're going to have to do equivalent fractions to see if the ratios and the rate of changes are the same. This one from -10 to -4 is an increase of 6. This is an increase of 4. This is an increase of 4. And this is an increase of 2. So what you have to do is you have to turn these into ratios. 3 to 6 ratio, a 2 to 4 ratio, a 2 to 4 ratio, and a 1 to 2 ratio. If these are all equal, this has a constant rate of change. All right. The reason it doesn't look constant is because they're jumping around over here. If this had been -5, -4, -3, -2, this would have been the same each time, because each time it increases by 1, this increases by 2. And that is the case for all of these. It's just that these were jumping around. So this one is also linear, even though originally it didn't quite look like it was going to be. All right, over here, oh, I like these so much better when they just go up by 1 at a time, because it's so much easier to tell if it's linear or not. These all go up by 1, so if these are all the same, this thing's linear, okay? Well, 35 to 41 is an increase of 6. 41 to 47 is an increase of 6, I'm hopeful. 47 to 53 is an increase of 6, and 53 to 59 is an increase of 6, and it is linear. I don't know why I care. Why it's not like better to be linear. Why do I even care? That's it. That's all the problems I expect you to be able to do in this practice. And so go on over to McGraw-Hill and finish the practice assignment and have a great time. I hope you enjoyed as much as I did. See you in class.